let's go over this again. So we start with the import, right? Import with the torch model, neural network in the torch, and here, this one is the optimization you need to import. Okay, so this is the OPTIM, which is the optimization method you need to import. And then the data. There are some different things between the Keras and the PyTorch. In PyTorch, I mean, if you remember in the ANN models, in the sklearn, you just need to prepare your X and Y, right? Separately, two different metrics or array, and then input to your models. But here, usually you'll use a data loader. Okay, so it's kind of a package to combine all these X and Y together, because we are working on the images. It's more complex, so using the data loaders. And then here, these are the data set that we're going to use, which is the handwriting digits. And then of course, the typical package for the metaplotted, we're going to visualize them. So device saying that in your computing environment, either you are going to use a CPU or GPU. So this code will say that if you are GPU, if you have GPU, which means that CUDA, which is the algorithm, the language for GPU, CUDA language from NVIDIA, they are available. Means that the PyTorch is supported by the GPU, so you can use that if it exists. If not, then you'll just keep in mind using the CPU. Okay? So this is the batch size I mentioned to you, right? The batch size for every time we try to train the models, we select the tiny portion of the images. So we select 64, means that we have 64 images. And then we select the learning rate at the beginning, 0.01, and epochs, as I mentioned, how many times of the training you want to do. So let's just do it 5 times. So during every training, every epoch, you will go over multiple batches, select all these 64 and times multiple batches, eventually equals to your overall size of the images. Right here, what we are going to do is some transformations. The concept is the same, like the normalizations. Okay? In the ANN, if you remember, we have those X, right? And you need to do the normalization for those input vector X. So here, what I'm going to do, what I'm showing you is do the normalization for all the images side, for all the images value, the pixel values. Okay, so it's the same as the normalizations. And then we'll try to download this data set and split them into the training set and the testing set. And once you have the training, including training images and the training labels, right, we combine it into the data loaders for the train loaders. And of course, we do the same thing for the test loader. Okay? So now here's the example. Right? Once I have downloaded images into my folders, and I just visualize for you with their label. So this is the ground truth. This is the answer. So we have, for example, input images here. Obviously, we know that is 9. So the label is 9. This is the ground truth Y. So you want to predict that Y. Okay? And input images handwriting digit 2. And you want the computer to say that's 2, so on and so forth. So you have the input images here and the label Y. So this is X, this is Y. Right, so now let's work on here. Our image size is, give me some minutes. I need to reround it. Right here, okay, great. that's continuing our work. So now here, these are the kernel, right? Okay, let's zoom in here. So I also write this for you. This is the convolutional kernel. And inside the convolutional kernel, you need to assign what is the input channel, output channel, kernel size, stride, or padding, just like what I've shown you, right? So, for example, our input dimensions here in the, input channel, not a dimension, it's just a channel. So here we just use 1, because the images we are input here is grayscale. It's not RGB 3 channel, it's just grayscale. Okay, so the input dimension here is 64 by 64 by 1. The size is 64, and the dimensions of the number of channels is 1, just the grayscale. Okay, so we assume that we're using 32 by, we use that 3 by 3 kernels with 1 padding, and the default stride is 1. And then we use 32 kernels. So you can imagine that eventually when your output, after this convolutional kernel, you'll get 32 channels. Okay? So maybe I go down to here first. You will better understand what I'm talking about. Here, our input images is 64, right? 64. And then we use the kernel size 3 by 3. And the padding is 1. So 64 minus 2 times 1 minus what? Minus kernel size 3. Divided by the stripe, which is 1. Right? So which is 64 minus 3 minus, it should be 32 by 32, not 64. Should be this one. Should be 32. For that handwriting digit, it should be 32 by 32. Okay, so 32 by 32, that's the input size. Minus 3 minus 3, which is what? 28? Is that right? Right. That's 27, 27 divided by 1 plus 1. So your output size is 28. Right? Is that okay? So after the convolutional kernel, the size is 28, and the channels depends on how many kernels you use. So here we use 32 kernels, right? So that's why you'll get 28 by 28 by 32s. Right? This is output after the convolutional kernel. And then we do the ReLU. ReLU is not going to change your size, just change your number within it. So still 32 by 28 by 28. And then we use the pooling. So maximum pooling size 2, stride size also 2. So it gives you 14 by 14s, right? Half of the size. Okay, we have seen that example. So here's the real world case. And now we are on the same page. Okay, now we are on the same page. And then here is the output, right? 14 by 14s. And then again, you use the pooling, so the size becomes 7 by 7. All right? So we are back on the track. And we use the flatten. So you have the neural network dot flattens, which is 64 by 7 by 7. So once you flatten, you get 3,136. That's the flattened output. And then you can work on the linear function again to make sure that eventually you have 10 outputs, because we want to do the 10 digits classifications. So here is the 10 output. Right? So this is summary for overall the output dimensions. Can help you to track all the input and output. Now, after that, you need to evaluate your models. So within your model.evaluate, you need to assign what is the loss functions. So since we are working on the classifications, you need to use the cross entropy. So this is a cross entropy loss. Then you also need to assign the optimization method. So here, when you work on the optimization method, I try to compare all this for you. Optimization with the stochastic gradient descent, with the momentum, with the RS prod, with the atom. So you can choose different optimization function. You assign an optimizers using optimize.sgd or .rsprod or .atoms. And then you also need to keep in mind that basically the SGD is what we have used so far as a naive gradient method. When you assign the momentums, so here you can change different momentums for the SGD to introduce so-called the velocity terms. So these are all the hyperparameters. Your learning rate, the optimization methods, the momentums, and even other like the gamma and the beta within the RS prod and the atom. You can tune them when you do the training and the validations, just like what you have done in previous homework. You should play with those parameters. Right, so after that, you can try to output your training loss, testing loss during every epoch. So this is just a typical things you need to do. Or you don't want to do that, it's also fine. Just make sure to follow the trend of those loss functions. So here I'm showing you the results. I ran this last night. So we just used 5 epochs. And then we already get a really good accuracies. For SGD, the training test is about 92% accuracies. But for the ADEN, it's like 99% accuracies. So I say that for even this kind of naive models, we just use 2 CNN units, right? You see that ADEN can perform pretty well. So I would recommend you start with the ADEN. Okay? Any questions? I upload this Jupyter notebook for you, so you can take a look at them and play with those algorithms. The most different things here compared to the next one I'm going to show you is the model is called the torch.nn. Okay? This is the neural network model, including the ANN, including the CNN, and all the functions you need. And now let's work on the other one, this one. So if you want to use the Google Colab, just turn on your Google Cloud. Just turn on the Google Cloud, and then you can find out the Google Colab. So you can ask in your Google Drive to turn on the new Colab, and the Colab will save the file as the same file you use in Jupyter Notebook, which is .ipynb. So here is the different deep learning package. The backend is so-called the TensorFlow. TensorFlow is the first version of the deep learning package from Google. So TensorFlow, you see that many times. And Keras use that TensorFlow as the backend to do the same thing. From the CNN layers, from the pooling layer, from the forward calculation, from the backward calculation. So pretty much the same, but you know the syntax may be a little bit different. So here I use the same data set for the 10 handwriting digits, right? As you can see here, the same data set. So you can download that directly, and this will be, I'm not going to run this again, but when you use the Google Colab, it will save directly to your Google Drive. Okay? So that's the convenience place. You can always find out those files. So this is the only thing I want to show you, the difference here. So previously, we just used in PyTorch, convolutional 2D, right? So here in the Keras, you need to define a model sequentially because it's layer by layer. So here you define a sequential model, and the first layer is the input layer, and then the convolutional 2D layer, maximum pooling layer, so on and so forth. And more easily, after every convolutional kernel, you can directly assign padding, stride, and activation functions. Okay? Concept is the same, just different syntax. Okay, so if you have some difficulty when you use these real-world models, you just ask ChatGPT. I think they can help you right now, very easy. So again, you can summarize all these architectures of your CNN. And we are working on the classifications, so the final output should be 10. 10 different digits, okay? And here, the only difference, this one, in the PyTorch, right? We use what? We use linear. So linear is the fully connected layer, the AMN models. In the Keras, it's layers.dense. Dense layer means fully connected layers in Keras. Okay? Right, so all the rest are the same. Train the models, choose your optimization methods. So here I choose Adam, right? After you define your model, you need to compile them in the Keras. So model.compile, make sure that you assign the optimization method. Here we use Adam, and we use the loss functions, again, the categorical cross entropy. Right, so these are the training, and the result shows you that, hey, the training 0.99, 99%, testing also 99%. The same as what we have seen here in PyTorch, 99% accuracy. Just the naive CNN. Okay? Alright, so this is an example for CNN working for the classifications. Next time we'll talk about the transfer learning, because you can imagine now we only have 2 units of CNN, and it actually involve a lot of parameters, right? Here, look at the final parameters that's trainable. 400,000 parameters. That's just 2 CNN units. In the Google DeepMind, large language model, AlphaGo, the deep learning model is trillions of the parameters. So you need an efficient way to train those models. Either select a huge number of data or even faster algorithms. So I will show you in the transfer learning, it will give you a more efficient result. You don't need a lot of data, but you can still get a really good result. Okay, let's start by here, and I'll talk about this maybe on Wednesday. So on Wednesday, after your presentation, if you still have time, I'll continue working on the transfer learning. Otherwise, we'll talk about on Monday. All right, see you next time.